Hi everyone. So we are going to go ahead with Werner's theory. That's another important topic in coordination compound. So Werner was a scientist who has really worked hard to give the structure of the coordination compounds. The structure what we have been talking about, that's the coordination sphere, outside the coordination sphere the counter ions, and within the coordination sphere the placement of metal and the ligands. So, how he conducted his experiment and came to the conclusion that the real structure of the complexes is the association between the metal and the ligands. So, there were few experiments done by Werner's which we are going to discuss over here. So, let us understand one by one. Let us say that the complex given to us is COCl3.6NH3. I'm not going to depth why this compound was taken. This was just an experiment conducted by him. Right now we are not using the convention of the complex which I taught you. Okay, remember that. Because with his experiment only we came to know how to write the formulae of the compound. Though all these terms I taught you before, but at his time, at his period of time, the convention of writing the complexes was in progress. So what he did, he took this compound and allowed to react it with AgNO3. So when silver nitrate solution reacts with any compound which contains chloride ion, we are very well aware that the precipitation of AgCl is seen, is observed, and these AgCl precipitated out is white in color. Fine. Now, how many ions got precipitated out? I'm talking about the chloride ions from the complex. Okay, that made a difference to prove that all those number of chloride ions which have come out in the form of precipitate, that is AgCl, have to be considered as counter ions, because in his theory you will learn Werner's theory. He said very clearly those ions which are ionizable are considered as counter ions, or we use the term called as primary valency. Wherein, on the other hand, he observed all those ions, whether it is positive, negative, or even neutral species, which could not get ionized. That means at any period of time when you see the process of ionization, they were closely bonded or associated with the central metal atom. So all such valencies were considered as secondary valencies. So let us understand this concept. For example, in experiment 1, he said that 3 chloride ions got converted to AgCl. That means 3 chloride ions are precipitated in the form of AgCl. So what could you understand from this? That means all those 3 chloride ions are acting as primary valency. So let us write here, I'm going to write over here for you. The primary valency was considered as 3. So primary valencies are basically your counter ions. What are they considered as? Counter ions, and they are present outside the coordination sphere. So how can I write this structure in the form of the complex which I taught you? Be very careful to make a note of it. I'm going to write over here. So CO, cobalt, is the central metal atom, and NH3 is the ligand, right? So I'm going to use round brackets for it because I have a number here, that's 6. Now since ammonia here, or we call it as amine, so don't get confused. So ammonia or the amine, which the term I'm going to use as a ligand, I have already made it clear before in the video. So these ammonia or the amine ligands are non-ionizable. That means they are associated with a metallic bonding, right? Not metallic bonding, sorry, coordinate bonding with the metal. So since they are closely associated with the metal, with the coordinate bond, they are considered as ligands. And the counter ions, that's the chloride ions, the three chloride ions which got precipitated out, are considered as primary valency, and that has to be cited outside the coordination sphere as Cl3. So this is how he understood to write the formulae of a compound. So if I ask you what is the secondary valency, that means you need to see the ligand over here. So which is the ligand over here? NH3. Why are we calling it as a ligand? Because ligands, I told you in the beginning itself, ligands are always found to be bonded with the metal atom with a coordinate bond. That means they are non-ionizable. Hence the secondary valency is 6 in this case and the primary valency is 3. Now let us understand the second example that will help you to understand it more easily. Now again here you can see COCl3.5NH3 and only 2 moles of AgCl were formed, right? So what can you understand from here? That means out of how many chloride ions are present or chlorido ligand is present, I don't know whether you are going to call it as a ligand or a counter ion. That I have to decide right now, right? So I am using the term chloride ions. Fine. So chloride ions are present over here and they are 3 in number. But out of those 3 chloride ions, only 2 got precipitated out. That means only 2 out of 3 are going to act as a primary valency. Fine. So if it is acting as a primary valency, I have to write them outside the coordination sphere. Fine enough. Now what is the central metal atom? Cobalt here, and amine is acting as a ligand. So how many molecules of amine are present? That's 5. Now one chloride which did not get precipitate out, okay, is going to act as a secondary valency. That means it is going to behave as a ligand, and therefore I'm going to use the name for it as chlorido. So here I'm writing here 1Cl which acts as a ligand, that's the secondary valency. So in this case, if I ask you what's the primary valency, your answer should be 2. And if I ask you what's the secondary valency, then your answer should be again 6. Why 6? Because 5 amine plus 1 chlorido is going to give you 6 as the number, which is the secondary valency over here. Fine. Now let us go ahead with third example. Okay. Now in third example, he found that this was the result. This was the result, that means COCl3.4NH3 when allowed to react with AgNO3, he could find that only 1 mole of AgCl got precipitated out. So when 1 mole of AgCl got precipitated out, it means what? That only 1 chloride ion is acting as a counter ion, wherein 2 chloride ions are not acting as a counter ion. They indeed behave as a ligand. So what is the primary valency here? Primary valency should be 1. What should be the secondary valency here? We are going to find it out. Now let us first write the complex structure. So again, cobalt, okay, is a central metal atom. Of course, amine has nothing to do with precipitation, so it is acting as a ligand. How many molecules are present? 4. So I have tetrastate, right? Then out of 3 chloride, only 1 got precipitated out. So what is the left of? Cl2. So these Cl2 are basically now called as chlorido, and one chloride ion is acting as a counter ion. So that's the structure of the coordination compound. So again the secondary valency comes as 6, right? Why 6? Again because of 4 amine and 2 chlorido. So these experiments, the 3 experiments which he conducted, made very clear that what exactly is meant by primary valency, what exactly is meant by secondary valency, and how the process of ionization actually occurs. So let us see what were the postulates of Werner's theory, what all I have mentioned. I have just written over here. Now see the first point. The central metal atom in the coordination compound exhibits 2 valency. Those were the 2 terms which I have been using, primary valency and the secondary valency. You can also call it as linkages. I also mentioned that primary valencies are basically ionizable. That means they are behaving as your counter ions, the term which we have already understood in the previous video. And they are usually satisfied by negative ions, but it could be positive ions as well. But in this example, he did not talk about positive ions. He was only emphasizing on negative ions. So we also have to pick this point up because his experiment was only based on chloride, right? So positive ions you just keep aside. Why I mentioned over here, so that you don't get confused with the complexes like K4, Fe, Cn6, wherein we have positive, that means the protons, the ions which are present are in the form of K plus, that is potassium ions, right? So keep it aside. So I'm going to just highlight this negative ions for you. Okay, when we talk about secondary valencies, we also understood that he very clearly made it, clear from his experiments that secondary valencies were non-ionizable. That means they can't be dissociated at any period of time. Whatever you do, you can't dissociate metal and the ligand association. So this point is to be noted down. Okay, and very important point, he said, those which I have already discussed before, all secondary linkages are basically your ligands. And ligands we know could be neutral or ions. Ions means it could be positive, negative, that means anionic, cationic, or it could be neutral as well. Fine. Another important point, because he wanted to give the structure, the shape, the spatial arrangement in the coordination compounds. So he gave a very, very important point over here. The secondary valency is fixed for any kind of metal which is associating with the ligand, and that will equal to be its coordination number, right? Very, very important thing to be noted down here. So coordination number, which we learned the term before, is nothing, something different number, and coming from where? It's just equal to the secondary valency. And all these examples which I worked out for you, the experiment which he did, you could easily see in all these experiments the coordination number was 6, because the secondary valency was 6. Hence he could made it very clear that, I will write down here, secondary valency is basically equal to coordination number. And once you get to know the coordination number, you can talk about the spatial arrangement of atoms or the ligands around the metal. Fine. Then another important thing I have already mentioned here about spatial arrangement. Fine. So this all hopefully is clear to you. And yeah, spatial arrangement since depends upon the coordination number, and I already mentioned in the previous video of mine that if coordination number is 4, right, then the shape could be either tetrahedral, right, or it could be square planar. Likewise, if the coordination number is equal to 6, then it is an octahedral complex. So you have to keep this in mind. It's a very, very important point. Fine, let us quickly go through the whatever I explained you. I have just summarized it over here. Fine, so here are few differences between primary and secondary valency. So primary valency, as I said, ionizable. Secondary valency is non-ionizable. Another very important point is it is usually satisfied by charged ions. As I said, it could be positive and negative, but in Werner's examples, what we mentioned before and what he shared with us according to the precipitation reaction was only talking about chloride ions, that is the negative ions. And here we also mentioned that secondary valency is nothing but the ligands, and which corresponds to the coordination number as well. Then primary valency does not help in deciding the structure of the complex. Its role is just to ionize, right? Secondary valencies plays a vital role in the spatial arrangement of the atom, as I discussed with you, 4 or 6. Tetrahedral, square planar in case of secondary valency is 4 or the coordination number is 4, and octahedral in case you are landing up with coordination number as 6. Henceforth, very, very important point, the last one I need to mention, that primary valency can also function as secondary valency. We understood in the last two examples, right? I'll just show you here. We go, yes. In these two examples, we learned that the counter ions, like for example, let me fix this for you. Here the counter ions, that means the primary valency was only 1. But the chloride ions were 3 in number. So out of 3, only 1 got precipitated out, and 2 others which were left behind were acting as secondary valency. So hence this is very, very important point to understand that the primary valency could also act or function as a secondary valency, but the other way round it can't be. That means the secondary valency at no period of time can act as a primary valency, because secondary valency, you should just keep in mind, is nothing but the ligands, right? So when secondary valencies correspond to the ligands, and we made it very clear, ligands can never be dissociated away from the metals. They are closely bonded with the metals with coordinate bond. Hence, secondary valencies can never function as primary valency. So that was Werner's theory, and let us also see the limitations, though it was a very good, step of Werner's to the world to propose the coordination compound structure, talk about the spatial arrangement, and he also gave a very clear indication, basically the demarcation between the secondary valency, the primary valency, the concept of coordination number. Yet there were few flaws in his theory. So what are the limitations of Werner's theory? Let us just quickly go through. It fails to explain the magnetic, color and optical properties. Though he was continuously speaking about the spatial arrangement, right? But he could not talk about the paramagnetic or the diamagnetic behavior. That we will understand later when valence band theory was given and crystal field theory was given, right? Likewise, he could not talk about the color, and we all know that D block we have studied, right? All transition elements exhibit color because they possess unpaired electrons and they undergo D-D transitions. But here he could not talk about that's the saddest part of his theory. Fine. He also failed to explain the reason why all elements do not form coordination compounds. And next very important thing is he also failed to explain the directional properties of the bonds. That means how are they spatially arranged? What could be the different isomers? What could be the exact geometry? That means though we understood that 4 means tetrahedral and square planar and 6 means octahedral, but that time he could not give a clear idea that how they are aligned in the space, like in the equatorial position or axial positions, diagonally placed. That we will be learning in the principle of isomerism. And very important thing, his theory could not explain the stability of the complex, as well as he could not give any idea about the nature of the complexes. So many drawbacks were there for this Werner's theory, and therefore later on, I'll just highlight here for you. Later on, it was the theory which is known as VBT and CFT, crystal field theory, could only give the clear idea about the spatial arrangement, magnetic properties, the geometry, the alignment, and so many other things. So basically we will follow CFT in the later videos, and that's very important theory. Lot of questions will be asked, and one of the most what you say, the flaw in Werner's theory was he could not give any concept about hybridization. He could not give a clear idea about hybridization, so he could not say anything regarding the shape or the geometry of the structure. So, geometry of the structure could only be well understood by using CFT or VBT. Hence, that was the basic and the major flaw of his theory. So that's all for the day, and just go through all the concepts, learn them well, because the coming up theories are very much aligned with what has been taught till date. So thank you all, and remain